Hello, calculus fans. Let's give a geometric interpretation of partial derivatives. We already have a geometric interpretation of ordinary derivatives. They represent slopes of tangent lines. Well, the same thing is going to be true for partial derivatives. Now remember that z equals f of xy represents a surface. That's the graph. So if the value of f of AB is equal to c, then we can say that the point ABC lies on the surface. If we keep y fixed by setting y equal to b, what we're doing is we're restricting our attention to the curve in which the vertical plane y equals b intersects S. We're going to call that curve C1. In other words, we can think of it as the trace of S in the plane y equals b. And similarly, if we take the vertical plane x equals a, that's going to intersect the surface in a curve C2. Both of these curves are going to pass through the point P. Here's a picture of what we're talking about. C1 and C2 are curves that lie in the surface. C1 is what we get when we keep the value of y fixed. C2 is what we get when we keep a value of x fixed. Those are curves that are in the surface. And as we'll discuss next, T1 and T2 are tangent lines to the curves C1 and C2. The slopes of those lines will be what the partial derivatives represent. So C1 is the graph of the function g of x equals f of xb. So that means the slope of its tangent line, T1, at the point P, is just g prime of a, which is the partial derivative of x evaluated at ab. And similarly, the curve C2 is the graph of the function g of y equals f of a comma y. So the slope of its tangent line, T2, at the point P, is capital G prime of b, which is the same thing as the partial derivative with respect to y evaluated at ab. So, what does all this mean? It tells us that the partial derivatives can be interpreted geometrically as the slopes of the tangent lines at the point P to the traces of the surface in the planes y equals b and x equals a. Now, in the previous example, we saw that partial derivatives can be interpreted as rates of change. So if z is equal to f of xy, then dz by dx represents the rate of change of z with respect to x when y is fixed. Okay, that's all for now.